We're going to go ahead and get started. Welcome and thank you for joining us. We're here bright and early in Las Vegas, and I know we have quite a few people watching online. We're here at the Ascend conference, and this morning we're going to be talking about the LOFTID technology demonstration, which is coming up on November 1st, and how it fits into our entry, descent, and landing technology development efforts here at NASA. So I'm going to briefly introduce our panelists, and then we'll get started. For folks in the room, if you want to ask a question when we get to that portion after remarks, you can just raise your hand and we'll have someone bring a mic to you to ask your question. For those of you watching online, you can use the Q&A function in the webinar and we will read your question aloud to our panelists. So when you are asking a question, please give your name and affiliation, and if you're directing your question to anyone in particular, please note that as well. All right, so I'm going to quickly introduce our panelists and then I will pass it off to our first speaker. So we have Trudy Kortes, Director of Technology Demonstrations in NASA's Space Technology Mission Directorate, Michelle Munk, Acting Chief Architect for the Space Technology Mission Directorate, and Ashley Korzun, LOFTID's Aerodynamics Database Lead. If you registered, you may have expected to see Neil Cheatwood, LOFTID's Principal Investigator, here as well. Unfortunately, he had some travel issues and he's not able to join us, but we will give you a great overview with the three of these panelists. So I will pass it over to Trudy to start us off.
Okay, well, thank you, Sarah. And thanks everyone in the room and online for joining us early this morning here in Las Vegas. So I think I can speak for all of us and say we're really excited to talk to you all about this today. We're really looking forward to the upcoming launch next week on November 1st at Vandenberg, along with JPSS-2, the Joint Polar Satellite System 2, part of NOAA's program. We're a rideshare along with them. And this is a culmination of a lot of work by our LOFTID project. So LOFTID is a project that is part of the Space Technology Mission Directorate. It's been led by Langley Research Center in partnership with the United Launch Alliance. I'll talk about that in a minute. And it's part of our technology demonstrations mission program. And what we do in what we call TDM is we develop technologies to the point where they are ready to demonstrate in what we say the relevant environment in which they ultimately need to operate. So we put things together at a system level, and then we demonstrate them. And I'll give you a couple of other examples aside from LOFTID. We have something on orbit now called the Laser Communications Relay Demonstration that we launched in December 2021 and is up there operating for about 2 years to demonstrate bidirectional optical communications from space to ground and ground back to space. We are developing solar electric propulsion thrusters at a 12 kilowatt power level that's never been done before. And we're getting ready to qualify those in spring of next year and getting those ready for flight as part of the Artemis program, specifically on the Gateway architecture. So we do things like that to enable future exploration missions, and LOFTID is a great example of that. And so what we're doing here, and Michelle and Ashley are going to give more specifics when they speak, but what we're doing here is demonstrating hypersonic inflatable decelerator. It's at the 6-meter level. It's a first of its kind. It's never been manufactured to that scale and put together, like I said, at a system level. It provides the primary structure. It's a decelerator. It withstands very high temperatures. And so next week what will happen is we'll launch on JPSS-2. It'll orbit the Earth one time. It'll re-enter the Earth's atmosphere. It will decelerate from, I think, like Mach 25 to about Mach 7. And then it will land gently in the Pacific Ocean off the coast of Hawaii. And so really what we're looking to learn here is, does it work, basically? And you can think next week as the Earth's atmosphere is like our giant test chamber next week. So ultimately the goal here with LOFTID is to be able to land very, very heavy payloads, very heavy hardware and even crew potentially on Mars, Venus, Titan, the largest moon of Saturn, anywhere that has an atmosphere, Earth, this technology will work. So we're really excited about it, really cutting edge technology. And then I'll just wrap my remarks by saying that this has been an outstanding partnership with many different organizations, frankly. Like I mentioned, NOAA, Science Mission Directorate, our partners there, but then specifically United Launch Alliance, ULA, actually approached us with this project many years ago. And it was really the idea came from Bernard Cutter. Bernard was the manager of advanced programs at ULA, and he was always interested in access to space and reducing access to space and the cost for that. And so he realized that the technology we were developing for our needs to go to Mars could very well serve their needs, and they're looking at this technology to reduce the cost of their Vulcan launch vehicle by being able to bring back the first stage engines of that. And if they can do that, when they accomplish that, in bringing down the cost of access to space, that's a win for NASA as well. It's a win for them, it's a win for us, and really a win for the aerospace industry as a whole. And so Bernard passed away in 2020 unexpectedly, and NASA and ULA in partnership decided to dedicate this mission to Bernard in his memory and his name. And we're honored to do that. So I think that concludes my remarks, and happy to take questions at the end. And to you, Sarah.
Thanks, Trudy. I'll let Michelle give her remarks next.
Okay, thank you, Sarah. So the LOFTID demonstration is a key milestone in our entry, descent, and landing technology development efforts, and we're happy that we're flying this mission in partnership with ULA and under technology demonstration missions. So within the Space Technology Mission Directorate, land is one of our 4 thrust areas, and entry, descent, and landing is one of our core capabilities. And as you heard from Trudy, our long-term goal is to land humans on Mars, and that will require about 20 tons of hardware to be landed at any one time. And that's about 20 times more than we've done so far with the Curiosity or Perseverance rovers. And Langley Research Center, being the lead in the agency for aerodynamics, recognized long ago, about 15 years ago or so, that we can't land heavy payloads on Mars, deliver them through the thin Mars atmosphere, as we have in the past with an aeroshell that's rigid and fits inside the launch vehicle shroud. So we need something with a big surface area to effectively slow down those large masses, and so the inflatable decelerator is a way to do that. It's stowed inside the launch vehicle and is inflated before we reach the atmosphere and allows us to get the deceleration that we need. So LOFTID is really a very unique and perfect demonstration of the technology because we will see Mars-relevant heating and pressure on the structure as we come in from low Earth orbit. So really excited about that opportunity to get those relevant environments. And the 6-meter scale is actually the largest aeroshell that's ever entered an atmosphere. So that is a big milestone for the agency, and it's a stepping stone for us. We demonstrated the inflatable decelerator at the 3-meter scale on the IRV-3 flight back in 2012 on a sounding rocket out of the Wallops Flight Facility in Virginia. But we couldn't reach the velocities that we're going to reach with LOFTID. But it did show us that the technology performed well and was very stable, and so we're really excited about this opportunity to go from 3 to 6 meters, and eventually for the Mars application we'll need to build about a 16-meter structure, and the ULA use of returning the rocket stages is somewhere in between 6 and 16 meters. So we have a very nice progression that we're embarking on here, and we're very excited about this milestone. The graphic that you're seeing now shows the Mars entry, descent, and landing sequence. So first you see on the upper right the vehicle outside the atmosphere with the rigid nose cap that really supports the structure before the inflatable is expanded. And then you see it inflating. This can take several minutes. We're not in a rush. We do it all before we touch the atmosphere. And then we get our full 16-meter to 18-meter heat shield. You see the graphic of the heating there. We see about 3,000 degrees Fahrenheit. And then our supersonic retropropulsion engines come on. These vehicles to support human Mars landing are so big and so heavy that we cannot use parachutes as we have in the past on every previous Mars landing. So we're just going to turn on our retro rockets, which we need to land safely anyway, and we're going to use those to help us decelerate. Then we land safely on the surface and retract the HIAD so that the crew can access the surface. So this is one concept. Of course, the Mars program really doesn't exist yet, and our Mars landing is several years away, but we do need to start working on these technologies now. These are long lead items, and it takes several years to develop these vehicles at this scale and test these technologies in the relevant environment, such as we're doing with LOFTID. So I'll stop there, and I'll turn it over to Ashley.
Thanks, Michelle. Before we start with Ashley, I think Trudy wanted to correct one thing she said about LOFTID.
Yeah, I think I said Mach 29 to Mach 7. I meant Mach 0.7. Big difference there. Thank you. Thank you for noticing.
All right, Ashley, I'll pass it to you.
Great, thank you, Sarah. So I'm going to talk a little bit about the concept of operations. What are we going to do on LOFTID? So as was mentioned, LOFTID is going to be a secondary payload launching on a ULA Atlas V launch vehicle from Vandenberg Space Force Base. It's going to be in the wee hours of the morning here coming up very soon on November 1st. The primary on this vehicle is the JPSS-2 weather satellite, of course. So when does the LOFTID mission begin? After the JPSS-2 satellite is delivered to orbit, then LOFTID is going to separate, and our mission really begins there, and the clock essentially starts once our vehicle is powered on, and the whole thing is going to take us about an hour. So as Michelle mentioned, the hypersonic inflatable aerodynamic decelerator, or HIAD, is going to be inflated exoatmospherically. We take our time, but it's still only going to take us about a handful of minutes to reach our full inflation pressure, which is what's going to allow us to handle all of the loads and environments we're going to experience during reentry. At this point then, LOFTID is also going to spin up to a fairly low spin rate, about 3 RPM, and begins to enter the atmosphere on a ballistic trajectory, so not any sort of active control, and spin stabilized. Real-time beacons on board are transmitting limited data during flight, so we are getting some information as we're entering, but a much more comprehensive data set is going to be stored both on board the vehicle as well as on an ejectable data recorder. So as Trudy mentioned, this ejectable data recorder, it is released from the LOFTID vehicle right about Mach 0.7, so definitely going subsonic by this point. After that happens, then a parachute is deployed, and LOFTID continues to slow down, and we will splash down in the Pacific Ocean. And the plans are absolutely to recover that ejectable data recorder, but to recover the reentry vehicle as well. So we'll have folks standing by, out in the Pacific Ocean, ready to retrieve those for us.
Great. All right, thank you. Now we're going to open it up to questions. So just a reminder for those of you in the room, please raise your hand and wait for the microphone to be brought up so that the folks online can hear your question as well. And then if you're online, you can put your question in through the Q&A function, and we will read it aloud. All right. Okay. I don't think we have any online questions just yet. Do we have any questions in the room? All right, bring in the mic. And please state your name and affiliation, and if you're directing your question to anyone specific.
Hi, yeah, I'm Paul Brinkman with Aerospace America magazine. And I'm not sure who to direct this to, but you were talking about future Mars missions that this might be used on. We have a number of them that are planned in the next few years. So can you be any more specific about what types of missions this would be used on?
So I guess I'll take that one. Right. So we have actually we're bumping up against the limit of the Viking heritage technology with the rigid aeroshell that fits inside the launch vehicle shroud. and the supersonic parachute. The Mars sample return mission is the next one on the manifest, and it has a very large and heavy lander, the sample retrieval lander that carries the Mars ascent vehicle with it. So, beyond that mass, we're probably going to be outside the box of what we've done in the past. So any future missions that deliver heavier payloads, such as logistics, preparing for humans, or very large scientific payloads, would benefit from the HIAD technology. The inflatable heat shield is very mass efficient, and anytime you can use the atmosphere to your advantage, it's a lot less massive than using propulsion. So again, this would be really great at Titan, Saturn's moon. It has a very thick atmosphere. You could use it at Venus for some sizes of payloads. It helps us at Mars to land at higher altitudes. So to date, we've gone to low spots on Mars because even that little bit of extra atmosphere that you can fly through helps you slow down and land safely. So some scientists are interested in going to the southern highlands of Mars, and HIAD would allow you to do that by decelerating you at a higher altitude and allowing you to land at what we would call sea level on Mars or higher.
And I'll just add on briefly and say, I think I mentioned this, but anytime we do technology demonstrations, we just, we remember they are tests and we have to learn from them and see, and then figure out next steps from there. And we work really closely with our stakeholders and our other mission directorates to kind of figure out timing of that, and then couple that up with, kind of budget, schedule, technical progress that needs to be made, to look at future mission infusion.
We have a question from reporters online. The first one comes from Jeff Faust at Space News. Are there any plans for testing larger inflatable re-entry systems, to get closer to the 16-meter diameter desired for Mars, or intermediate sizes needed for ULA's Vulcan?
You want to take that for scale up?
Yes, we would, as I said, we would like to progress in size from the 6-meter scale of LOFTID up to the 16 meters. We have in our development strategy scaled up flight tests. We need to, for Mars application, add more robustness, other features that the eventual Mars landing vehicle will need, such as integrated guidance, navigation, and control, and transition to the retropropulsion stage. So those features will not be tested in LOFTID. So those are things that we need to do in the future to test the even subscale or full-scale Mars vehicle. As far as ULA, returning their rocket stages, they will need somewhere on the order of about 12 to 14 meter scale. And so as their future plans progress, they will be flight testing and using HIADs on that scale, which will really help us to demonstrate kind of in a stepwise fashion the capability to go up to the Mars vehicle. In addition, if ULA employs this as their method of rocket stage return, we'll get several flights of the hypersonic inflatable aerodynamic decelerator. Those will be instrumented and give us increasing data sets about its performance in the flight environments that we can use to build confidence and make improvements. And they will also sustain the base of vendors, the industrial base that is used to manufacture the inflatable decelerators. So we see this as a wonderful partnership and a way to maintain the supply chain and keep the learning going as we progress for the long term towards a Mars mission.
We have another question from Sumit Shitye from Hasya Kata Official. How long will the LOFTID mission run?
I can take that one. So from the time we power the LOFTID vehicle on until we splash down. It's going to take us just about an hour.
All right, any other questions online or in the room right now? Well, I have one. So Ashley, I know you talked about how the data is going to be recorded on the aeroshell and on the ejectable data module, and your role really comes into play once we get that data back. Can you tell us more about what you're going to be looking for in terms of LOFTID's performance when you get the data?
Yeah, absolutely, Sarah. So we're going to have, as Michelle mentioned, we've got lots of temperature and pressure measurements. We also have cameras on board that are going to be looking at the structure. The vehicle is a decelerator, so we want to see it function as a decelerator. It needs to slow the vehicle down, but we need to have stable flight while this is occurring as well. So we will be getting telemetry and be able to reconstruct the trajectory that LOFTID flies, and we'll actually be able to reconstruct and validate our predictions of the vehicle's performance. We're also going to be able to essentially validate against the thermal protection system performance. There's a flexible TPS that makes up the heat shield that allows LOFTID to survive these environments, and will also allow us to verify and validate our models for the structural integrity of the system. So lots of amazing data that we just can't wait to get back.
Since you mentioned the TPS, behind us you can see that we have our display article. I think it's about 1 point something meters, so smaller than actual scale, of course, but you can see some of the layers of the aeroshell. So those kind of tan tubes are the material that the actual tubes are made of, and then the flexible TPS, and it's a little hard to see on the camera, but there's several layers of it that you can see exposed on that anatomy article.
We have another question from Zach Albert from TLP Network, the Launchpad News. Could you talk a little bit more about what new technologies or techniques had to be created for the inflatable decelerator? It looks like a rather simple idea, but we know reentry is the furthest thing from easy.
You want to start, or you want me to?
Go for it.
I'll start. Ashley will fill in. Well, several technologies, protecting fibers or textiles essentially from an environment like this is not something we do all the time in terrestrial applications. So it was a particular challenge to find the right material to to work with the weaving industry to actually weave the fibers in a very uniform, repeatable fashion, develop the models of the inflatable structure itself. One of the features of the HIAD is that it is a pretty, basic structural model, so it's very predictable in its behavior, and therefore we think very scalable, which makes it fantastic for all types of applications. One of the other challenges is the thermal protection system. As Sarah mentioned, it has several layers. Getting those layers, one, so that they would take the environment, the 3,000 degrees Fahrenheit that we'll see, but also be able to be handled. So our PI likes to call those the illities, the flexibility, handleability, packability. And so that's been a challenge to really minimize the volume, the packed volume of the various layers, but also making those layers something that you can easily handle in the laboratory and during fabrication. We have folks who actually stitch together the flexible thermal protection system with very exotic fibers. So lots of component technologies, lots of hands-on fabrication and talent, really, that is evident in our article.
Yeah, I mean, the list goes on too. The gas generator system, this is what actually inflates the HIAD itself. There's been a lot of development work and working with small businesses to figure out how do you do this, and then how do you do this in the space environment. The other cool thing that comes to mind is there's a lot of instrumentation all throughout the different layers of the heat shield and all over the structure, and a lot of those are fiber optic. So kind of new types of sensors, new ways to take these types of measurements is ultimately what's going to make this mission so valuable, that data that we get back.
All right. Do we have any other questions in the room? Right here. Can you bring the mic?
Thank you. I'm Ben Ionata from Aerospace America. First, I want to make sure I understood some of the numbers you gave. So to land, is it 20 metric tons?
It is.
Metric tons,
20
okay.
metric tons, yes.
You need a 16-meter diameter.
Yes. That's what we believe, yes, currently our concepts, yep.
So the idea is that someday 20 metric tons could be a lander with people aboard.
Could be.
The current architecture has the logistics and the ascent vehicle, as well as any habitation elements being landed by the hypersonic inflatable decelerator-based system, yes.
Okay, good. And then could you kind of touched on this, but just kind of walk down memory lane on some of the things you've learned and include how many years this has been in development and what are some of the adjustments that you've had to make. And as you do that, if you could make clear what, NASA personnel did compared to what ULA personnel have done or are doing, that'd be good.
Okay. I can start. I think probably Ashley has more of the details, and unfortunately we don't have our principal investigator with us today. So, Ashley's on the team, but I haven't lived it day to day, so I'll do the best I can. We might need to follow up with Neil Cheatwood, but along the way, I think, as I mentioned, the scaling up is a challenge. Finding the right materials that reduce the packing volume and the mass. I recall that one of the particular challenges has been the flexible inlets where the gas goes into the torus structures, because those have to be crunched up and packed during launch. So that's been a particular development area. So as I said, in 2012, we flew the IRV-3 at the 3-meter scale. IRV-1 was, I don't remember the year, but we had a launch vehicle anomaly where we weren't ejected properly. So is that IRV-1? Is that correct? Two, okay. So we did IRV-1. And then IRV-2, we had a failure. We got to refly it in IRV-3 in 2012. And really since then, it's been, we've followed this progression of ground scale up and then flight test. And so we started with small articles, such as 1-meter scale, and then the 3-meter scale on the ground. It gets tested in wind tunnels, in pressure vessels. We do arc jet testing on the thermal protection system. So all of the components get tested, but as Trudy mentioned, at the system level, we then put it together and have the opportunity to fly it in a somewhat relevant environment. With the inflatable reentry vehicle experiments, the IRVs, we were looking mostly at stability and just, would this thing work? And now that we have confidence in that, we're looking at the scaling. I think, the contribution from ULA has really been the opportunity and the pull and the opportunity to actually do this larger scale flight test in a public-private partnership. And they have actually, scarred their vehicle, their stages for the incorporation of the inflatable decelerator in the future. So they've really brought this opportunity to the table for us. I think it'll be a very seamless technology transfer into usage as we go forward. And so, that's been a very valuable part of taking this from, concept to actual application. We've also worked with mostly actually small businesses on the actual construction of the article and the technologies that go into that, the various, the weaving, the strap construction and materials, the thermal protection system layers. And so, but there are limited suppliers right now, so we're hoping to expand that industrial base as we see this in repeated use. So really, ULA is the pull and the driver for that.
And you asked timeline, I think. So Michelle mentioned earlier that this type of technology has been in work for a long time. This specific project, LOFTID, started in October of 2017, and will, launch about 5 years later, which is actually pretty good for a technology demonstration mission. But as she mentioned, the predecessors to this has been happening for a long time, 10, 15, years.
Anything to add?
Great. Any other questions online?
We have one more question from Smit again at Hasya Kara Official. What are the biggest benefits of using an inflatable decelerator?
Well, I mean, it packs up and fits inside fairing, and provides primary structure. The strength of this inflatable is incredible, what else can we talk about here?
Well, I really, one thing I didn't really mention specifically is that the system is very tailorable. So we have the inflatable structure, which can be, tailored to the load that you're going to see upon entry into different atmospheric environments. And then the thermal protection system is almost it is a separate subsystem that can be tailored in terms of the layering and the types of materials that we're using for different applications. So, Mars heating isn't all that high. But if we are going to Venus, we have a very different heating environment. So we can tailor that system. Another really interesting feature, and I think very unique feature of the inflatable decelerator is that, as Trudy said, it packs into the launch vehicle, and it's not, it doesn't have a back shell. So if you are familiar with all the missions we've flown to Mars, or really any entry capsule thus far in our history, it always has a forebody and a back shell. So the payload is entirely enclosed. That means going on an interplanetary mission, you might have challenges with communications. It may be difficult to do science along the way. You have to manage that thermal environment in that fully enclosed aeroshell. And so with the hypersonic inflatable aerodynamic decelerator, it's packed up in front of your vehicle. You are completely open to space. You can communicate, you can manage your thermal loads perhaps more efficiently, and do observational science during your journey. And so it's a very flexible platform that allows, actual more return from each mission potentially. So it really has wide application across the solar system.
All right, any other questions right now? None online, any in the room? Okay. Well, thank you all. I think we're going to go ahead and wrap up, so I'll just leave you with a little bit of information about the launch. As folks mentioned, LOFTID is launching and demonstrating on November 1st as a rideshare with NOAA's JPSS-2 weather satellite. The launch is scheduled for 2:25 a.m. Pacific, that's 5:25 a.m. Eastern, and that's the start of the 36-minute launch window. So we will have coverage of both the launch and the demonstration, including some of that real-time-ish data that Ashley mentioned, and that starts on nasa.gov/live at 1:45 a.m. Pacific, 4:45 a.m. Eastern, and again, that's November 1st. So we hope that you'll tune in and watch the launch and demonstration, and if you want to learn more about LOFTID, you can visit nasa.gov/LOFTID. Thank you all.